Welcome back. In the last video, we talked about how to use vertical slices, and step one was to make sure that your curves are labeled as y equals a function of x. If they're not, you could isolate y if you really want to use vertical slices. But in the next section, in section 5.2, we'll see what to do if you don't want to isolate y, but you have x isolated instead. All right, so area using horizontal slices. For a certain region, it is easier to divide the region using horizontal rectangles and horizontal slices. For example, consider a region bounded by curve x equals a function of y. So let's put that one here. X equals a function of y. And on the other side, another one of these. Right? And let's say we want to look at this region right here. All right, if you have a region like this, then the more efficient way of actually splitting it up into slices is not to use vertical slices. That would keep getting cut off and you'd have to split it into tons and tons of different parts. And so the easiest way to split it up into thin sticks is to use horizontal sticks, so horizontal slices. All right, so this is a horizontal slice. And so their width of one slice would be, let's take this one, it would be h of y minus j of y. Notice that bigger numbers are this way. And so it's going to be the one on the right that's bigger. So it's going to be right minus left. Now the height is very, very thin. It's a small change. It's a small change in y. So I'm going to call it dy. And so the area of one slice will be h of y minus j of y, or right minus left, times dy. Okay, so it's the same idea as what we've done before. It's just that now the roles of x and y are flipped, right? So the area of the region bounded by x equals h of y and x equals j of y between y equals c and y equals d is the integral from c to d of h of y minus j of y dy. So now y is my variable, and I'm assuming that h of y is the bigger one of the two for the entire interval. The more helpful way of thinking of this is to think of it as right minus left dy. All right, so if you want to use horizontal slices, you need to first make sure that your curves are labeled as x equals a function of y. Again, if it isn't the case, you can isolate x. Then you find all intersection points algebraically between each pair of consecutive intersection points. Find left and right by plugging in a point between these intersections. Then you can give a rough sketch of the region. And finally, you set up the integral and you evaluate it. And you need to split the integral up whenever right and left switch. Right? It's the same principle, but just flipped on its side. All right, let's try example 5.2.1. I want to find the area enclosed by x equals y squared minus 4y and x equals minus y squared plus 2y. All right, so I have two curves that are described as x equals something. So I'm going to use horizontal slices. If you wanted to use vertical slices here, you'd have to isolate y, and that's kind of complicated, and we'll do it in an example just to show you how complicated it is. Here, I actually get two different functions of x for each one of these curves, so that would involve four different functions of x. All right, so don't need to do the first step, it's already done, and then I'm going to take, I want to take algebra to use to find the intersection points. So I need x equals y squared minus 4y equals minus y squared plus 2y. Don't hesitate to stop and do whatever part you feel comfortable. I'm going to send everything to one side to get a quadratic equals 0. Then I'm going to factor whatever's in common. I'll get y minus 3 left. And so we get y equals 0 or y equals 3. If y equals 0, x equals y squared minus 4y equals 0 as well. And if y equals 3, then y squared minus 4y, that's 9 minus 12 minus 3. All right, let's put those in, let's put those in the graph. All right, so we have 0, 0 right here. And then x is minus 3. This is a bit confusing, right? We're used to having x here and y here. It's flipped, so x is minus 3 and y is 3. So 1, 2, 3. Here's my second point. Oh, sorry, minus 3. All right, I want to figure out which of the two parabolas is right and which one is left. I need to plug in a value between the two. Remember, y is my variable, so I'm going to plug in a value of y. I could plug in y equals 1, that's fine. That's between the two. So at y equals 1, the first x is 1 minus 4, it's minus 3. And the second one is minus 1 plus 2 is 1. Right, so let me use a choice of color here. If I use blue here, that's the first one. At 1, it's at minus 3. And if I use green for the other one, at 1, it's at 1. All right, so I don't really need to know more than this. I'm just going to sketch it. Of course, in this case, since they're parabolas, I could actually get a closer picture by finding the vertices of, but really, all I need is this. All right, so that's my region. Let me label the curve. That's going to help me. So this one we said was x equals minus y squared plus 2y, and this one is y squared minus 4y. All right, perfect. We need the integral from c to d, right minus left, dy. I haven't talked about C and D much. These are, C would be the smallest value of y for the whole region. And so in this case, that's the lowest value of y, so C is 0. And then D would be the biggest value of y for the whole region. And so here, D would be 3. So I get the integral from 0 to 3. Right is minus y squared plus 2y. Left, right, so right is on this curve and left is this curve. So left would be y squared minus 4y dy. All right, for most problems, we'll just ask you to set it up. So this would be enough. If you want to integrate it, I recommend simplifying first. You'll get minus 2y squared plus 6y dy. I actually integrated it for you and got 9. If you want to check that you can do it yourself, go ahead.